the pulley, part 1. Here we have a book on top of a table. The book is attached to a string across a pulley which is holding up an empty box. The mass of this book, let's say, is 4 kilograms, and the mass of the box that's hanging is 1 kilogram. Let's do a force diagram for the book BK. Well, its weight is 40 newtons to one significant digit, therefore the normal force is 40 newtons. Okay. The force of the string is creating tension, which is pulling the book, but if the book is on a frictionless table, then this must be the net force, an unbalanced force. There's no friction to balance it out. The net force is equal to the tension. The mass of the book times MA, net MA is net force, is equal to tension. But what is that tension? This book is clearly going to accelerate or slide across this frictional table solely because the tension in the string, the force of the string, is yanking the book to the right, accelerating it to the right. Can we calculate this tension? Well, let's do the force diagram for the hanging box. Its weight would be 10 newtons to one significant digit. Its tension would be 10 newtons. That would give us, though, a net force of 0. But if this object is accelerating, then this can't be correct. The acceleration of the book, the acceleration of the box must be one and only acceleration. Therefore, my tension must be less than my weight. I must have net force downwards on my box for the box to accelerate downwards. Just as the book is accelerating to the right, the box must be accelerating down because my whole system accelerates. The whole system accelerates, not differently at either end, at the book and the box end. The whole system accelerates with one acceleration. So my tension up must be less than my weight to give me the same acceleration that the book has. All forces diagrams must be in balance. These are second law problems. My net force is the mass of the box times A by Newton's second law. So I have two net forces to give me the same acceleration of these two different masses. Tension minus weight is my net force. Adding up the forces gives me a net force. My weight is negative because it is down. My tension is positive because it's up. Therefore, my net force must be negative because my weight is down, my net force is down. They must have the same sign, negative. But these tensions are the same, so I can make a substitution. What I've done here is I substituted in for tension equaling the mass of the book times the acceleration, where tension minus the weight is now mass of book times acceleration minus weight. The mass of the box times A, that's my far right there, the net force is what this equation is equal to. The net force on the box is equal to the net force on the book minus the weight of the box. That's simply by substitution of these two net force equations. Let's clean this up a bit and rearrange. So weight of box is mass of box times gravity. Now let me solve for my acceleration. Acceleration, take that out from those two sides. Mass of book and box is mass total. So this is equal to my acceleration. Acceleration, by rearranging these equations and do it yourself to get the same result, is equal to the weight of the box divided by the total mass of book and box, the mass total of the system. This makes sense. The weight of the box, the hanging bucket or box, is what's making this system accelerate. What's happening is the weight of the box is pulling the system. It's pulling the system against the total weight. So that makes sense. Let's check it out. We can always look at extremes in physics to see if it makes sense. If I increase the weight of my box, I have to increase the acceleration of my system. Well, that makes sense. That seems to be the way it works here. My weight of my box is mass times g, m total is the total masses. So I've increased the mass of the box, and I only have a little mass of the book in comparison. Essentially, it's mass of box divided by almost the mass of the box, plus the little tiny amount of mass of book, which means this ratio approximately equals g. That's what you expect. If the box is much, much heavier than the book, then the system is almost in free fall. In the extreme, the box is far, far heavier than the book, then the system is essentially almost equivalent to being free fall. It has acceleration of just about g. Looking at the other extreme, if the box is very light compared to the mass of the whole system, because the book is much heavier than the box, then my acceleration approaches 0. If the book is far heavier than the box, and I almost have no acceleration. So I have a range of acceleration from 0 to my acceleration being being equal to g. So I have the greatest acceleration as it approaches g, and I have almost no acceleration when the books and the boxes have very different weights. So I can see my equation has a sensible relationship. Okay, let's get this out of the way now. So using the values I have here, the weight of the box is 10 newtons, the mass total of the book and the box is 5 kilograms. That gives me acceleration of 2 meters per second squared. Therefore, my tension was equal to my net force on the book. Mass of book times acceleration, that's 4 times 2, which gives me 8 newtons. So I have 8 newtons of tension. So my acceleration is 2. My net force in the box is the tension up minus the weight down. That's a negative net force because the net force is the same direction as the weight. Tension is 8 newtons. So I can substitute it in. Same tension, 8 minus 10 is equal to 2 newtons. 1 times 2. Mass of the box is 1 kilogram. Acceleration is 2. 1 times 2 is equal to 2 newtons, which is the same thing as tension minus weight of box. So it's consistent. Both ways of doing it, I get the same result as I should. Let's say the box now falls for 1 meter. The box goes from rest and it falls down 1 meter. So I can use a kinematic equation. Initial velocity, acceleration times time. Initial velocity is at rest, so it's 0. So it falls 1 meter, 1/2 acceleration of 2. So the time it takes to fall is 1 second. So after doing these force diagrams and solving as a second law of force diagram, imbalanced force diagrams, I can solve for my acceleration, knowing my masses and knowing the weights of these objects. I was able to solve for the acceleration. But once I solve for the acceleration, I'm right back to previous material using kinematic equations. I can see how long it takes for this box to fall at that particular acceleration if I measure it falls for 1 meter. Does it make sense that with an acceleration of 2 meters per second, it falls for 1 second for a fall of 1 meter? Well, an acceleration of 2 meters per second is 1/5 of g. It's 1/5 the g acceleration, roughly 1/5 of 10, 1/5 of 9.8. Well, we know that something in free fall with a full acceleration of g falls 5 meters in 1 second. This only fell 1 meter, but only has 1/5 of g. So falling 1 meter is 1/5 of 5 meters, which takes 1 second at the rate of g. 1/5 the rate of g, it takes 1/5 the time, or it falls 1 meter in 1 second. So it works out.